Hello viewers, I have already discussed problem number 1 and 2 on Picard's existence and uniqueness theorem. Now I am discussing problem number 3, 4, 5 and 6. Problem number 3. If S is defined by the rectangle mod x less equal to a, mod y less equal to b, so that the function f of xy equals to x square plus y square satisfies the Lipschitz condition, and also find the Lipschitz constant. So it's a very easy problem. Let x, y1 and x, y2 be two arbitrary points in the rectangle S. Then we have mod of f of x, y2 minus f of x, y1 equals to mod of x square plus y2 square minus x square plus y1 square. And then we can get mod of y2 square minus y1 square. This is mod of y2 plus y1 into mod of y2 minus y1. Since mod y less equal to b, that is mod of y2 plus y1 less equal to mod b plus mod b, since mod y less equal to b. Okay, and this term remain invariant, equals to 2b into y2 minus y1. This shows that the Lipschitz condition is satisfied. Hence the Lipschitz constant is here k equals to 2b. Okay. Problem number 4. Illustrate by an example that a continuous function may not satisfy a Lipschitz condition on a rectangle. It's a very important problem. Illustrate by an example which is a continuous function but may not satisfy a Lipschitz condition. Okay. As for example, let us consider the function f of xy equals to y to the power 2/3 on the rectangle S such that mod x less equal to 1, mod y less equal to 1. Here we have considered this rectangle. Here f of xy is continuous in the rectangle S because mod y less equal to 1, that is y lies between -1 to +1 closed interval. Hence in each value on that interval of y, f of xy is defined and finite. Hence it's a continuous function. But del f by del y equals to mod of 2 divided by 3 into y to the power 1/3, which is tends to infinity when y tends to 0, because on that interval mod y less equal to 1, y equal to 0 is a point. Okay, hence this is tends to infinity when y tends to 0, and this 2 shows that the Lipschitz condition is not satisfied by the function f of x equals to y to the power 2/3 on the rectangle S. It's a very important problem because it's an example which is where the function is continuous but does not satisfy Lipschitz condition. Okay, problem number 5. Show that the f of xy equals to 4x square plus y square on R such that mod x less equal to 1, mod y less equal to 1 satisfies Lipschitz condition. It's a very easy problem. Here f of xy equals to 4x square plus y square del f divided by del y, that is mod of 2y, which is less equal to 2 since mod y less equal to 1 for each xy belongs to 1. Hence f of xy satisfies Lipschitz condition. Now I will discuss a very important problem which is related to CSIR net June 2015. For initial value problem, dy by dx equals to y square plus cos square x and y0 equals to 0. Determine the interval of existence of its uniqueness of solution given that R is the rectangle containing origin R equals to xy such that 0 less equal to x less equal to a and mod y less equal to b. Also is given by a greater than half and b greater than 0. Okay, the largest interval of existence of the solution predicted by Picard's theorem is given by 0 less equal to x less equal to h. Okay, and here h is defined by minimum of b divided by m comma a, and m is defined by supremum of f of xy. Here the given function is y square plus cos square x, and R is xy such that mod x less equal to mod y less equal to b. So m is equals to supremum of f of xy, that is 1 plus b square, because mod y less equal to b, that is less equal to b square, and cos squared x, mod of cos squared x less equal to 1. Hence m equals to 1 plus b square, and h is defined by minimum of b by m comma a, that is b by m is equals to 1 plus b square comma a. Let us find which is minimum this term or a. Okay, let h of b equals to b divided by 1 plus b square. For extremity h dash b equals to 0. Here solving we get b equals to plus minus 1, and h double prime b is equals to this h double prime b at b equals to plus 1, we get minus half, which is less than 0, which is a maximum value at b equals to plus 1, and h double prime b at b equals to minus 1, that is equals to half, greater than 0, which is a minimum value at b equals to minus 1. But we have to maximize h, thus h equal to b by 1 plus b square at b equals to plus 1. b equals to plus 1, this is maximum value. Hence h equals to, we take b equals to plus 1, that is h is equals to half. Since h equals to minimum of b by m comma a, that is minimum of b by 1 plus b square comma a, and minimum of b divided by 1 plus b square is equal to half comma a. Since by the given condition a greater than half, so here minimum of half comma a greater than half, so let us assume that a equals to 1. Okay, since a greater than half, so let us choose a equals to 1, that is minimum of half comma 1, that is minimum half. Okay, thus h equals to half. So y of x exists on the interval 0 less or equal to x less or equal to h, less or equal to h, so h is equals to here half, so we get the interval 0 less or equal to x less or equal to half. Hence the largest interval in which there always exists a solution is 0 comma half. Here is an important note: if asked only interval in which solution exists, if asked only interval in which solution exists, answer will be any subset of 0 comma half closed interval. Okay, if here only interval where solution exists, then answer will be any kind of subset of 0 comma half closed interval. Okay, I will also discuss on Picard's existence and uniqueness theorem, problem number 7, 8, 9, 10, etc. Thanks for watching.